Lecture number 17, Redox reactions, part 1. So far we've been sort of classifying these chemical reactions, and we've looked at precipitation reactions, where we go from aqueous solutions to something that's solid. We've talked about these acid-base reactions, where we take an acid plus a base to neutralize them to form a salt and some water. And this is the sort of the last general type of chemical reactions we're going to talk about, redox. So these redox reactions, redox is short for oxidation and reduction. Right? So these are classified by a transfer of electrons. So we're not necessarily looking at the states changing, but we're looking at transferring electrons. So the charge of those individual atoms or elements are changing. So if we look at this reaction here, H2 plus O2 gives us H2O. Excuse me. We see that the hydrogen is losing electrons that become positively charged or more positively charged. So we call that an oxidation. The oxygen is gaining some electrons to become more negatively charged. We call that reduction. So oxidation is the loss of electrons, reduction is the gain. Or the way I remember it is Leo goes Gur. Loss of electrons is oxidation, gain of electrons is reduction. So we're going to follow these transitions of changes in electron movement by looking at something we call the oxidation number. So the oxidation number is sort of the charge that atom would have if in the molecule if the electrons were completely transferred to it. So we can talk about an oxidation for something that's not really an ion, right? But we're talking about completely transferring those electrons to it. Right? So there's 6 rules for these oxidation numbers that we're going to have to learn. The first one is that free elements, anything in its elemental state, as you would find it as an element, has an oxidation number of silver. So like sodium solid, potassium solid, lead solid, anything in its elemental state with 0. But also those things that are diatomic, like hydrogen, oxygen, nitrogen, fluorine, all of those are diatomic. So when they exist as a diatomic molecule, we call has an oxidation of 0, including phosphorus, which is that tetraatomic. The second rule is that for monoatomic ions, those things that are ions, the oxidation number is equal to the charge of that ion. So if we look, we have lithium as a positive, so it has oxidation number of +1. Iron 3+, its oxidation number is +3. Oxygen is a 2-, its oxidation is going to be a -2. Right? So whatever the charge is on that ion, the oxidation number is the same. And here is sort of why I write the oxidation numbers versus the charge. So if I put the charge, I always say the number and then the positive. So the iron would be a 3+. That helps me distinguish the fact that its oxidation number then is a +3. The next rule is that the oxidation number for oxygen is always -2, except for when it's in a peroxide, then it's a -1. So we'll be able to recognize those pretty easily. So oxygen is usually a -2, except for a peroxide, -1. And the next rule, the oxidation for hydrogen is a +1, except when it's in a binary metal compound. So if it is listed second, making it a anion, then we would call that as an oxidation of a -1. Those are fairly rare, but you need to remember that if hydrogen is listed second in a binary compound, but there's 2, then it is a -1. All group 1A metals, so those alkali metals are all a +1. Group 2 are +2. Fluorine is always a -1. The rest of them can sort of vary. Right? So alkali metals always +1, just like their charge. Alkaline earth metals are always +2, just like their charge, and fluorine is always a -1. Everything else, we can the sum of those atoms' oxidation number has to be the charge on the overall molecule. So the molecule has no charge, it's neutral, 0, then all the oxidation numbers have to be equal to 0. If it is charged, like in this case, then we see all of the sum of those oxidation numbers have to be a -1. So let's talk about CH3 or HCO3-. Because of the rules, oxygen has an oxidation number. It's not peroxide, so it's a -2. Hydrogen, again, this is in a metal diatomic, or binary, excuse me. compound, so it is a +1. So now we have the oxygen and the hydrogen oxidation numbers. So the carbon we can figure out from that. So the whole thing has to equal a -1. So we have 3 times the -2 for oxygen, which is a -6, plus the 1 for hydrogen equals, plus some other number has to equal a -1. Do that math, we see in this compound the oxidation number for carbon is a +4. Right? So with these simple rules, we can now determine the oxidation number of anything. So by looking at the oxidation numbers of the entire reaction, we are then able to determine what is being oxidized and what is being reduced, or if that is occurring in these redox reactions. So if we look now, again, remember the loss of electrons is oxidation, the gain of electrons is reduction. So if we look at this reaction, zinc solid plus copper sulfate, aqueous goes to zinc sulfate aqueous plus copper. We look at the zinc goes from a 0 to a +2. The copper goes from a +2 to a 0. So we can break those two in their half reactions, and we see because the zinc lost electrons, it is being oxidized. Right? And the fact that it's being oxidized is causing something else to be reduced. So the zinc in this case is what we call the reducing agent. The copper goes from a 2+ to a 0, so it is gaining electrons, so it is being reduced. The fact that it is reduced is causing something else to be oxidized, so we call the copper 2+ the oxidizing agent. So these agents are causing something else to do whatever its name is. So an oxidizing agent is accepting electrons, which means it's being reduced and causing something else to be oxidized. The reducing agent is donating electrons, so it is being oxidized, and the fact that it is being oxidized is causing something else to be reduced. So the oxidizing agent is reduced, causing oxidation. The reducing agent is oxidized, causing reduction. So we have to remember that when we're talking about these agents, it's in reference to something else, and it's opposite of what that element is undergoing. So based on this changes in oxidation number, we should be able then to recognize these redox reactions. In the next lecture, we're going to talk about how to balance these, because the way we balance them is slightly different. But for now, we should be able to recognize those. I just want to leave you with this, that there's one common example. So if we look at a breathalyzer analysis, excuse me, a breathalyzer analysis is a oxidation reduction reaction. So we have this potassium dichromate solution, which is orange. When we blow into it, we cause this species to go from the chromium to go from a +6 to a +3. So it's gaining electrons, so it's being oxidized. And by that, we're actually causing something else to be reduced. That alcohol is being reduced. So in the case that this dichromate is being oxidized to the 3+ chromium, we are actually seeing a color change. And the amount of color change that occurs is directly related to the concentration of the ethanol alcohol in that breath. So that's a real life application of these types of reactions.
Dad, I done did it.